Welcome to the Explainer. Today, we are tackling a mathematical tool that is so powerful it is literally hiding in plain sight. It's at the heart of everything from your favorite video game graphics to the economic models that shape our entire world. We're talking about the Matrix.
So, let's start with a big question. Imagine you're juggling a dozen interconnected problems all at once, and each one affects all the others. How would you even begin to untangle that mess? What if there was a way to just lay out all that complexity in a single, simple grid and find the solution in one clean, logical process? Well, there is.
So in this explainer, we're going to go on a little journey. First up, we'll meet the Matrix, get formally introduced. Then we'll learn the basic rules for how to handle them. We'll cover the 3 legal moves you can make to solve these puzzles. And then, this is the good part, we'll put them to work with a powerful strategy called Gauss elimination. And finally, we'll uncover the deeper secrets a matrix can tell us about what a solution even looks like.
All right, let's dive right in. What exactly is a matrix anyway?
At its core, a matrix is really just a grid of numbers. Seriously, think of it like a spreadsheet for algebra. It's an amazing way to take a messy-looking system of equations, strip away all the variables for a minute, the x's and y's, and just focus purely on the numbers themselves. We arrange them in this neat little block that we can then work on systematically.
Okay, so now we know what a matrix is. Let's get into the fun stuff. What are the basic rules for how we can play with them?
You'll be happy to know most of the rules are pretty much what you'd expect. Adding 2 matrices, it's like adding 2 shopping lists. Multiplying one by a single number, well, that just scales everything up or down. But matrix multiplication, now that's a whole different animal. It's got this specific row dances with column process, and you know what? This one special rule is what lets matrices do these incredible things, like rotating 3D objects in your favorite game.
Okay, now this next part is absolutely crucial. See, to solve a system using a matrix, you can't just go in and change numbers however you want. You gotta follow the rules of the game. And it turns out there are only 3 specific legal moves you can make that let you simplify the puzzle without ever changing the final answer.
And believe it or not, these 3 moves are all you need. That's it. You can swap any 2 rows. You can multiply an entire row by some number, or, and this is the real powerhouse move, you can add a multiple of one row to another row. They're called elementary row operations, and they are the only tools you need to crack the whole system wide open.
So let's actually see one of these moves in action. So right here, we're taking the first row, multiplying it by 2, and adding it to the second row. See how the numbers in that second row changed? It might look different, but the actual solution to the original problem is still locked inside. We've just taken one small step to make that answer a whole lot easier to find. And that is the whole idea.
All right, we've got the pieces, we've got the rules. Now for the payoff. Let's see how this all builds towards a real solution, using a classic, super powerful method called Gauss elimination. The strategy here is actually, it's surprisingly simple and kind of elegant. We use our 3 legal moves with one very clear goal, to create a triangle of zeros in the bottom left corner of the matrix. Once we get the matrix into this super simplified state, it's called row echelon form, the answer practically just falls right into our laps.
Okay, so here we go. Here's our system, all set up nice and neat in a matrix. You see that 2 in the top left corner? That's our first pivot element. And our first mission is to use that 2 to turn the -4 right below it into a big ol' 0.
And here is the magic. We perform one single row operation. We add 2 times that first row to the second, and bam, we hit our target. The -4 is now a 0. Just like that, the matrix is simpler, and we are one huge step closer to the solution.
And look what that little 0 did for us. The bottom row now represents a really simple equation. 13 times our second variable equals -26. We can solve that in our heads, right? The variable has to be -2. From there, we just plug that value back into the row above it and solve for the next variable. It's this beautiful domino effect called back substitution.
But hold on, finding the solution is just one part of the story. Sometimes a matrix can tell us something even deeper, even more fundamental, like what kind of solution we're even dealing with.
To figure this out, we use a concept called rank. Now, don't let the name intimidate you, okay? The rank is basically just a count of how many truly useful independent equations we have left after we've done all our simplifying. It tells us the real, true complexity of the system we started with. And this table right here, this is the ultimate decoder ring.
By comparing the rank of the main matrix, that's A, with the rank of the entire matrix, answers included, that's A:B, we can diagnose the whole system. If the ranks don't match, the system is basically lying to itself. There's no solution. If they do match and they equal the number of variables, you found it, the one, single, unique solution. But, and this is where it gets really cool, if the ranks match but are less than the number of variables, it means the system has some wiggle room. It means there are infinitely many solutions. The matrix tells you everything.
So, in the end, what we've learned today is way more than just a technique for solving equations. The matrix, it's a language. It's a language for understanding complexity itself. It's the hidden engine behind computer graphics, economic modeling, AI. It gives us this fundamental way to organize chaos and find these really elegant solutions. So now that you understand the power that's locked inside these simple grids of numbers, what complex problems will you see differently?